So welcome back to System Software. We are really close to the end of the semester. Today we're just going to go over some special topics. I want to show you a little application of some of the knowledge of how the compiler works to see how a very classic software exploit works. It may not be something you could use today, but because of their protections, but we can turn all those off and actually see it happening. And then next week, I'll get you a practice exam that will look very much like your exam on the exam day, and we'll do review on that all next week. So anything on projects, anything on homework, and I'll give you all the details about the exam then. Okay, so before we get into the lecture topic, I'd like to cover a couple of things. So first, I'd like to go over the homework and any project questions you have. So maybe let's start with the project. Questions on the project? Yeah. What's that? Speak up a little bit. So I noticed several people pointed out bugs in the .s files. I think don't use the .s files. I don't know why those have bugs in them. We're not going to be grading you on the .s file. We're going to be grading on the output of the assembler. If you have specific questions about them, I'll upload specific examples of what my compiler outputs. Yeah. I'm sorry, say again? Well, okay. So this is, so I think the question is, how do you test your compiler? So this is how you actually use the compiler. You build your compiler, and then pass a simple C file into it, and it'll give you a .s file. So that's your compiled output. So you guys wrote simple C. And you're taking in it, and that program's input is a program in the simple C syntax, and the output should be an assembly file. And here's how you actually test the result of your compiler. In order to test the result of your compiler, you have to take that assembly file, compile it into an executable, and then run it. And that will test that at least some inputs that you test are giving you the output that you expect. And so you build it just like you would any other program that you have, because you're effectively replacing GCC with a different compiler. But if you use GCC on your output, the assembly file, GCC knows how to run the assembler and link it and everything. So you just build the output of your compiler, and that'll give you an a.out file, or you can use all of the common GCC flags. And then once you run it, in order to see the return value of main, this is how you see the return value of main. Let me show an example of that. So here's my if.c file. Pass it as input to the compiler. Once you've built your compiler, make sure you rebuild it whenever you change it. Pass it into simple C, and if written correctly, you should just be getting assembly code as the output, if you see that. So all I did was run simple C and pass some simple C program as the input, and it'll just spit out assembly code. And that assembly code is assemblable. You can turn it into a binary and actually execute it using the existing system tools you have. on your system. So I'm just going to save the output. Oh, you can't see that because this is off the screen. So here I am just taking the output and saving it to a .s file. So here's my .s file. And GCC will look at the extension and actually compile it for you. So if I just run GCC on that assembly file, I'll now have a.out file produced by GCC. And you can do things more nicely, like use the -o and all that. And then when I run it, there's no I/O. I didn't give you any support for I/O, although you could actually link with a C program and do I/O. But right now, the only way to view the output is look at the return value of main. And the return value of main is the exit code. To view the exit code, you use this little bash magic, and it'll show you the exit code. So here it's spitting out 3, and if we look at our input program, this is one of the ones where somebody on EdStem pointed out that the assembly file given was broken. I unfortunately cannot update your GitHub repo. I can only update the one you cloned from, and apologies for giving you busted assembly files. But I think the best advice is just ignore those and ask me if you want examples. There are some examples on the website, I think. But yeah, that was the input program, and it was supposed to return 3. If the assembly program is equivalent to this input program, we should get 3 as the exit code, as the return value. Does that help? Does that make sense? Oh, yeah.
I was wondering if you could elaborate a little bit on the description for closure call expression in the project description for project.
Sure, yeah. Project 3, right? Project 3. Okay. So for the minimal project I've asked you to do, you can just assume there's always one argument for functions. Otherwise, it's a little more complicated. It helps to have a couple things open. It helps to have the calling convention, and also the AST description. So let me open those. So here is the syntax of the call expression. It has an ident and it has a list of arguments. And the list of arguments is a linked list where the data elements are just another expression. Okay. So as an overview, the way this will work, so if you recall, well, let me actually show an example of a function call here, if I have one. So here's the simple C for a simple example of calling a function. This has 2 parameters, but you'll only need to implement one. So for the function call, all that needs to happen is passing the parameter to the function, And so in our calling convention, the first parameter is always passed via RDI. So every function call will always just pass whatever the expression's value is to RDI, and it'll call the function and it'll save the return value. But in order to get the value of this argument here, so let's make this the simpler version. In order to actually get the value of this argument, we first need to generate code that's going to compute the value of that argument. So I'll make it a little less simplistic by adding an add expression. So here's my example. And here's the assembly output. So this is all the code that will compute the arithmetic plus expression. Yeah. Might be a problem with func. So let me diagram what the call expression looks like. So if we've got f of 1 plus 2, then if we look at the tree structure of this, we've got ident, which is f, and we've got args, which is a list. And the args list will contain each element in the list will contain an expression followed by another args list. In this case, there's only one expression here. So there's only one argument, so there's only one expression in the list. So just like before, the idea here is to, when we generate the code for the call, we just outsource the job of generating the code for the expression to the appropriate code generator. So the kind of code template for call will be whatever expressions you need, whatever the expression is, followed by code to store the first argument. There's only going to be one argument in the example I've given you. So code to store the argument. And then the actual function call is literally just using this call mnemonic and assembly and the name of the function. The assembler will handle all of the actual address. The assembler and linker will handle that for you. But you can just give the name of the function here. And then saving the return value. And in our convention, the return value is given in RAX. So this is really all the code that needs to be generated by the call expression function. So this is the call expression. This is the call expression node. So in order to implement this, all you need to do is call CodeGen on the first expression. And then once that's returned, because if you use our convention of storing the intermediate values on the stack, the top of the stack will hold the result of that computation at runtime. And then all you need to do is pop off that value into the parameter. The first parameter is RDI, the RDI register. Generate the call instruction, and then because a function call is also an expression, to follow our convention, we push the intermediate result onto the stack with push. Questions on that? So we need to do several things. We need to get the first argument. We need to generate code for that argument. We need to pass the parameter, make the call, and then save the return value. So how do we get the first argument from the tree? We can look at our AST specification to tell us how to do that. So it's in args. And so how do we get the first element of this linked list? Or how do we get the data from that first element of the linked list? So args is an expression list, and this is its type of the expression list. Yeah, how do we get the first argument? So if we have our input expression, args is our list, yeah. Yeah, exactly. So this is how we get the first argument in the list. Okay, so we know how to get the first argument. So knowing that we have this expression that we want to generate code for, how do we generate code for an expression? Yeah, exactly. Code gen expression, and then whatever this arg is. And so I'm trying to use this kind of program refinement style where you give yourself all of the individual pieces that you'll need, step by little, and then build up the function. Okay, so once this code has been executed, we should, if it's correctly written, then we should have generated the assembly for 1 plus 2. And if you haven't implemented the binary expression yet, you can just use int expression, which I think has been given to you. And so that should be correct, and you won't have to worry about what the argument syntax type is. And then for passing the parameter, as I mentioned, to satisfy the calling convention, we want to have it stored in RDI. And because our call expression convention is to always the last thing to push the intermediate value onto the stack, we can just pop it directly into RDI. And so you can just use the macro I've given to you to do that. And then similarly, we can make the call using the macro. So how do we get the name of the function? Well, we look at our structure here, and ident is how we get the name. So that generates the code for the call expression, and then saving the return value is, according to our convention, just pushing that resulting value onto the stack. So just push RAX. Questions on that? Let me make sure I actually got this right. I didn't miss anything. Oh yeah, so my code has the way to do it with like all of the arguments, but I think this is it. Other questions on the project? Yeah. For CodeGen Func, you can really just look at CodeGen main, and it tells you almost exactly the same. The only difference is use the name of the function given, and so you look at the AST structure to get the name of the function. There's only one argument in our simplified version of function calls, so you only need to insert the argument for whatever the first argument is and use the AST to get the name of that from the tree because it's going to depend on how the user defined it. And similarly, when setting up the getting the parameter, so at least in the scheme that I've recommended to you guys, all the parameters are in the stack frame as well. And so just copy that parameter onto the stack. Generate, and I missed the generate code for decalist, but you can see it there. Generate code for the statements, generate code for the expression, and then just save set the return value by taking the intermediate value that's on a stack and copying it into RAX. And then all of the other cleanup for the scoping and the prologue. But it's virtually identical to CodeGen main. Yeah.
So I understand that there needs to be testing with GCC and
Yeah.
comparing return values to what they should be. But,
Yeah.
that approach, I believe, at least like in my practicing, it requires the entire function is finished first before actually executing. Is there any way I can test the program
Mm-hmm.
like line by line? And instead, like I usually just compare ASC the .s files, but it's like they're not really where there should be a moment with no one else.
Actually you don't have to have the whole program written in order to test. The key is so are you writing your own test cases? So if you write your own test cases, then you don't have to use the parts of the code the parts of your compiler that aren't written yet. So the key is to design test cases first that are crafted to just execute the code that you need to execute. And it should be possible to, pretty sure it should be possible to execute, like, you can start with this, I modified it, but you can start with the very simplest, just like main return 0. And that should compile correctly, and then you can build from there. So then you can add codegen func without calling it. You can just add codegen func and inspect the assembly output. Then you can add call expression and inspect the assembly output and then start running it. So you should be able to do this without you should be able to generate your own tests for this. If that makes sense. Yeah. Mm-hmm.
The stack aspect, so for the offset, would you be looking at the right side?
You mean the offset into the stack frame? Excuse me. Yeah. Yeah, so you generate the code for the right-hand side, just like we saw for call expression. That's like always the same. And then it'll be stored onto the stack, and so pop it into some register. And then the difference for the left-hand side, so this is R values versus L values. The L values are addresses to store into. And as I think I went over, I hope it was recorded. But I think it was part of one of the homeworks, homework 11 maybe. The difference between storing to a pointer versus storing to a variable, they're both storing to a memory address. So this was the distinction between x equals 3 versus star x equals 3. So I think this is project 3, and this is project 4. I don't want those to blend. So this is the L value, and it's always going to be an address no matter what. The difference between the L value of a pointer dereference and the L value of a variable. So what is the difference? So how do I find the address of a non-pointer assignment? Yeah. Oh, I mean in the compiler. So how does the compiler generate code? So what's the code? How do you generate code for assigning x to 3? So assuming we have a stack frame already set up where this is RBP, and then we have x, a slot for x here in offset -8. Yeah. Yeah, so you this move 3, this is how you move whatever the left-hand side is. And in your real compiler, this would be an intermediate value on the stack. But from the homework, the key is how do you find the address of x? And for function local variables, this is stored on the stack. And if you remember, there was all this very specific syntax for doing this memory indirect addressing. But this is how you get the address of a variable on the stack. And the confusing part about the pointer is that you still want to get this value, but you want to store not, so for this case, you want to store it here. But for this case, you want to store it to wherever x is. Well, actually, let me do a different stack here. The stack frame is going to look the same for star x. The difference is that the stack frame for the value in x is going to be some memory address. It's going to be some memory address that's going to point somewhere else in memory. And when we do this, when we assign to a dereferenced pointer, we want to store this value here, not here. So we don't want it stored here. Make sense? So in order, yeah, go ahead.
You can store it in the RAX.
You would have to first get the value of x, store it in some placeholder register, and then move 3 into the address pointed to by RAX. So if you're just dealing with project 3, all you need to do is figure out what this offset is. Actually, all you really need to know is this offset, because there's already a macro that will move to an offset for you. So you just need to know the offset of x. So you just have to look this up in the symbol table. And so the idea here is that to find the left hand, find the left hand address, you just get the name. You look at the expression, you say, all right, is this an ident expression? So here you can just assume it is, if that's easier, but you can also do like a test to see if it's an ident expression. And then if it's an ident expression, you can get the name of that identifier from the AST tree. And then once you have the name of the identifier, you can look up its offset with that lookup offset. That will find this number here. Once you have that number, you can just move whatever the right-hand side value is that you got from generating code and popping it off the stack into whatever the offset is onto the stack. So sorry, go ahead. Yeah, you'll pop in order. So to make this closer to what our actual compiler is doing. It doesn't matter what the right-hand side code is. This will be it'll just be some expression that you call the code generator on in order to get this assembly code. But per our convention, we always store all expressions, intermediate values on a stack, and so in order to get that value, you can pop it off the stack. So yeah, you would pop first to get that value, and then find the offset of x. So this is our code. This is the code that generates the assembly that will compute 3. I mean, it's easy to compute 3, it's just move immediate. But this is the code that will generate the right-hand side. And pop will get the intermediate value into some register for you. Then in order to get the offset, you just get the name of x and put it to lookup offset. And it'll give you whatever the offset is. So let's say in this case, it's -8 per our previous stack. Yeah, and then you move to offset. So move to offset will generate this for you. It'll generate, I need some more space here, but it'll generate move, you give it whatever the value you want to move to it is, and then you give it -8, and it will generate this assembly for you. So this is move to. And so, I mean, you don't have to use these helper methods if you'd like to kind of figure out the assembly on your own. But this is what will get called. I mean, it won't be -8; it'll be whatever you found the offset to be. And so once you have this down, the Project 4 one should be a little easier. You just need to first generate a move to copy whatever the value of X is into a register. And then instead of moving into the stack frame associated with X, instead you move to the address that X is pointing to. All right, good questions. Yeah, these are kind of like fine details of yeah. All right, other questions on the project? I think project 3 is due. Oh, project 3 is due today. Project 4 is due next week. Remember, there's a very lenient late policy. If you're late, you can still turn it in after the deadline with a very minor late penalty. There are bonus projects that you can get lots of points back. So yeah, don't be afraid to finish this. Don't be so worried about the deadline. I have like a grade submission deadline, so we do have like an absolute deadline for the course. But I don't want you to be too afraid about, like sort of soon artificial deadlines. Keep working on it. Yeah, question. So if is it the assembler that's giving you the undefined reference?
No, it's like the compiler.
Your compiler is that? Yeah, it's sort of hard to debug here. I'd say come to office hours or ask on EdStem, and I'll walk you through it. But use the classic debugging practices. So make the smallest test case you can that still has the bug. Trim down your test case. Make sure you're not just using our test cases. Copy it, trim it down, and then use print statements or a debugger to figure out where in your code the bug is happening, or at least around where the bug, and then just step through one line at a time. And it should reveal itself without you having to rack your brain too much. And so I promise you basically turn a really hard debugging problem into a really simple one. This is like the key to debugging. If you're trying to debug hundreds of lines of code and you don't know where, you're giving yourself a very hard time. The key is to turn a hard problem into a simpler problem. That might take longer to do, kind of like if you knew the answer, but the key is you don't know the answer. And you'll be surprised how much easier it is to see what the bug is once you have kind of narrowed. It's like a surgeon putting like a hole in their sheet to just focus on the part they're operating on. You do the same thing for yourself. You isolate the thing you're working on and just step through very carefully one at a time. And the bug will be much, much easier to identify. And you'll be like, oh, that was such a simple thing. The key is finding it. It's like a needle in a haystack problem. That's what makes it seem hard. Yeah?
Just to confirm, your final exam will be over by 9:50 a.m.?
Yes. Yeah. So technically we have from 7 a.m. to 9:50, but I figured that was kind of early. And so I'll make the exam fit into basically an hour. I haven't figured out the format yet, or whether it's going to be in person or online. Kind of leaning to online. I don't know. Does anyone have a preference? Who wants in person? Does anyone like in person? We got one. Who likes online? Wow. Okay. Sorry. So yeah, but let me. You'll know next week. All will be revealed next week. Yeah.
So if we get the project report done early, can you email it to me?
Yeah, absolutely. Yeah. That's a good point. So there is no kind of late. There's no late option for the fourth one because it's just the end. It's like, well, I want to try to get grades in early and finish everything up, so everyone has their grades very early, and you can still submit after that and come to office hours and everything. like if necessary, I'll have time that week to like go over everyone's grades and everything. But yeah, you can submit early and email the graders. All right, other questions on the project besides like, your specific, I know you probably have lots of, bugs you're banging your head over. But yeah, still come to office hours, use EdSTEM, use that debugging technique that I've exhorted you guys to use, and it will be easier. It'll just be more tedious, but I'd rather have boring than hard, in my opinion. Okay, should we look at the homework? Who wants to look at the homework? Okay, let's look at the homework. Okay, so this was less than, the less than operator. And we have this example here of x minus y, where x is an RAX, y is an RBX. I wish this screen were aligned. And then we want the results stored in RAX. What assembly sequence could we use? All right, so let's start with this exact example. Or actually, yeah, we can just use, I didn't tell you how to generate it. It was just, how do we generate code for x minus y? All right, so what assembly instructions can we use to test values? Or what assembly instruction? How do we do logic tests in, compare, And how do we do different behavior if compare, if compare says this is true or this is false, how do we execute different code? Yeah.
Compared to the literal zero. If it's false, check.
Oh, right, yeah, that's true. So that's true for true and false. Once we have the result of that comparison, how can we, so if this were, say, embedded in an if statement, although I didn't ask you to do this, and this was like return 1 versus return 0, how would I take different paths in the code? Yeah, the jump. And so so there are lots of jumps. What jump might we want to use, or what options do we have? So comparing 0 is also possible. Actually, no, in this case, I don't think there's a way to do this with compare 0, but what jump conditions? Yeah. J what? G, okay, so we've got several options. We have JG. What's G do? Well, JG would be true also if it's not equal. So what is yeah?
JG is for jump with greater than.
Right, so JG is greater than. So can we use greater than to test this? Yeah.
Be greater than or equal to.
So another option is greater than or equal to. I noticed nobody said less than, which is interesting, yeah. You could use less than as well. And there's also less than or equal to. So we have one vote for using greater than or equal to and less than. I don't think we can use greater than or less than or equal to, at least not with how more work. But why is it possible to use either, or can we use either of these? Who says JGE is possible? Who says JL is possible? Interesting. So those who didn't say JG, why is JGE possible or not possible? Yeah. Yeah, it's the opposite of less than. So just like last time when we were looking at disjunction, you could compute the negation of, you could compute the negation of less than, and the negation of less than is greater than or equal to y. So depending on whether you wanted to branch if true or branch if false, you could use either. You just have to negate the result instead. Okay, so I'm going to use the JGE option, I guess, to confuse myself. But it's also kind of more commonly, I guess, what compilers do. All right, so we have x in RAX and y in RBX. And we know we're going to have to do some kind of compare. I'm going to try using the JGE version, and we need some label to jump to. All right, so how do I compare these two things to see if they're greater than or equal to? What are the arguments to compare? Say again, yeah? RBX, say again? That's a good question. So RBX, so this is AT&T syntax, so which register is the destination register normally? RAX, the right one. And compare is basically just to subtract, where the destination register doesn't get updated, but the ordering of the parameters is still the same. So if you put RAX on the right, it'll be RAX minus RBX. And so, another way to think of this is that you could rewrite x, this test to x is less than y, to be x minus y is less than 0. And so that's what jump less than will check. Jump less than will check this. And similarly, if we want to test x not less than y, this would be the same thing as, well, I can just do the logical switch here, where it's not x greater than y, which is the same thing as saying x minus y is greater than 0. So not this. Move this down, give myself some space. Okay, so we've got a comparison between these two parameters. The order is swapped for AT&T syntax. And then we're going to jump if x is greater than y. So this is jumping if x is greater than or equal to y. And so I will, if x is greater than or equal to y, we'll jump to this label. So what should the resulting value be if x is greater than or equal to y of this? Yeah, go ahead. 0. Why 0? Because the condition is not true. We've inverted the condition, and we've checked for the condition. So the condition is true, but because our inverted condition should give us the opposite of what our result is, then we should, the result of this should be 0, which is, I think, what I asked here, right? What the result stored in RAX. So how do we store 0 into RAX? Move. And we can overwrite RAX because we're not using it anymore for y, or at least in our compiler scheme. Okay, so what if it's not greater than or equal to? What if it's less than? What's the next line of code that will be executed? Yeah. Move 1 to RAX, yeah. So the branch won't be taken. It'll move 1 to RAX. All right, are we done? What's the problem here?
You're going to assign RAX is 0
Right, so if x is indeed less than y, we'll execute this move, and then the next instruction will be this move 0, overwriting the result that we wanted to generate. So we need an unconditional jump to move past the if branch, or the true condition branch, the label branch. All right, questions on this? And if you wanted to do the the JL version, you would just swap these values. So you're negating the condition, which inverts the result. So you would just swap these values if you do the JL version. Yeah.
If we do JL, does the compare order have to change the same?
Oh, so if you changed the order, that would be checking. So if we were to do compare RAX, RBX, that would be like comparing Y to X and whatever you put in here. So if you had done JL, that would be checking if Y is less than X. So you could still do this. You could, because because you know that you can prove that X less than Y is equivalent to Y greater than X. So you could, if you swap these arguments, then you can use a different test. You could use JG or JLE if you swap the arguments, if that makes sense. So because X less than Y is the same thing as saying Y greater than X, so you basically swap the arguments, right? If you swap the arguments, then the test would be, is Y greater than X? That would be the equivalent test for X less than Y. And so just like here when we were testing X less than Y, we could use JL or JGE, because those are inverses of each other. If we swap the parameters, then the question is Y greater than X? So the two tests that we can use are, is Y greater than X, or the inverse, is Y less than or equal to X? So I guess to complete out this little kind of math proof here, this is also the same as Y less than or equal to X, and the negation of that. So, I mean, one thing to observe here is that there are lots of different programs that are equivalent to each other. There's lots of assembly programs that are equivalent to the same input program. So it's up to the compiler writer to decide which one to use. And usually these decisions are based on optimization reasons. So are there ways to reduce the number of instructions? Here, I don't know if it matters so much. I mean, I guess if you knew that a certain branch was not going to be taken more often, then the compiler might be able to generate, may be able to pick the next instruction to be the most frequently executed one, if the compiler could determine that, or if there were tuning information to do that. And there are actually in C compilers, there are ways to say this branch is more or less likely, and the compiler can use that information to change the ordering around of branches. But anyway, that's a little outside the scope of this class. Yeah?
So what compare does is it subtracts the first argument from the second one?
That's right, yeah. It's equivalent to a subtract. It's a subtract where, so it's the same thing as subtract, but the resulting, this parameter is not saved. The result of the subtraction is not saved in the destination register. It just has the effect of updating the state of the rest of the machine, which is the flags register, which records whether it's a 0 or less than. And as a little exercise, if you want to prove to yourself, a machine, in order to do inequalities, the machine only needs to know how to compute equals and less than. So I'll leave this for a little exercise, or maybe a bonus exercise if you want to do the proofs for it. But I assert to you that we can implement equals, not equals, less than, greater than or equal, and less than or equal. So I assert to you that I can implement all 6 of these operations using these comparisons only. Yeah.
Do you actually need equals?
I don't know. I think so.
Curious what order the offering to do. Like,
Oh, do a test?
why-
Oh, yeah, that's true.
why you're gonna ignore it.
That's true.
Or-
Yeah. If you can prove that, yeah, prove that too. So a little bonus exercise. Write the proofs, the so-called proofs, that each of these operators can be boiled down to, at most, equals and less than. It's a fun little exercise to do, and you can show it. So you still have negation. You know, you can still do negation like this by just changing what value gets moved. But yeah, try this. It's a little fun exercise to see that these are equivalent. All right, other questions on the homework? Okay. So I'd like to give a quick overview of some principles of software security. For some of you, you may have seen this before. If you haven't, this may be an overwhelming amount of terminology, but I kind of want to get it into your minds. Security is a big area in computing. Many of you may go into security. UCF also has, I think, one of the largest cybersecurity clubs, Hack UCF. So if you're interested in this, then you can go to them, and they do competitions and training. I am by no means a kind of a software attack expert, but I want to go over some of the software security stuff, but then show an exploit that you can now understand if you understand how the compiler works and how the machine works. And so I stole these slides from somebody else who made really nice software security slides. And I just want to kind of give you a quick overview of the world of software security and then show you an exploit that's based on how our compiler works. So one kind of glib way to talk about software security versus just like writing code is that when you're trying to implement a program, your goal is to make the program do what you want it to do. So a lot of your debugging is around, well, this program is not doing what I want. How do I make it do what I want it to do? One glib way to talk about software security is instead of trying to make the program do what you want, it's to try to make the program not do what it's not supposed to do. And so these sound like they could be inverses, but if you only consider valid inputs, the inputs that you expect, well, these aren't really inverses. So if your program, if you only think, well, your program's only going to take integers, and you believe the user is only going to give you integers, if they then give you a string, well, your program may crash. You may get a seg fault. And if you're being very rigorous about your correctness, you should account for all possible inputs as well. But yeah, you can think of this as software security as making sure the software is not doing anything bad with the inputs. So who's seen the CIA framework, confidentiality, integrity, availability? Okay, so let's ask. Okay, that's good. So this is like information security fundamentals from like decades ago for like there's physical security, which is, like guns, dogs, concrete, ways to like protect physical security. But digital security, information security is it's related to physical security because if your information is stored in a physical space, well, that matters. But kind of researchers, I think government researchers, decades ago, came up with this 3-axis principle of information security. And there are 3 aspects to this: confidentiality, integrity, and availability. And so confidentiality is probably what you think of when you think of software security. You got an email from some website that said, hey, your data's been leaked, somebody broke in and they stole your information. They were not supposed to see your credit card number or your social security number. So that's confidentiality. But what you might see less often is integrity and availability. So let's say somebody went in and they changed your address to be their address. So whenever you order something expensive online, it goes to their address. And so, well, that is confidential as well because they could probably see your old address maybe. But integrity is also important because you need to be able to trust that the data is the same as who provided it to you. So the website needs to trust that the address was not overwritten with an attacker's address. And availability. So this is your classic denial of service attack. So if you have some important banking information and an attacker can just like shut down the website, but now you don't have access to your banking information anymore, and you might overspend or something like that. So when questioning whether a software system is secure, it's not enough to just say, so if somebody tells you, well, this is 100% secure and we're going to solve all your security problems, maybe grab your wallet because they're probably trying to deceive you. In order to understand whether something is secure, we need to have some definitions of what security and safety are. And so you can almost think of security as a kind of risk cost, the benefit cost, or what do you call it? Cost-benefit analysis, where for like a company, the expense of adding the security may outweigh what you actually secure from. So for instance, you could say, I have the best encryption in the world, no one can break it, but if an attacker can come in and just smash your hard drive, well, technically it's not secure. It violates availability or integrity. You don't have your data anymore. So you need to define the scope of what you're trying to defend against. So maybe you're not trying to defend against, say, a nuclear war that destroys the entire world, which you may not be able to defend against just through software tricks. But you need to define what your security posture is, and define the attack surface. What is part of what the things you're trying to secure? So maybe you have a safe in your house, but your neighbor next door doesn't have good security, and somebody digs a tunnel into your safe or something like that. Well, your neighbor's house is maybe part of your attack surface, but you don't really have control over it. And so in the security world, whenever you see people make assertions about security, if they're being kind of honest and ethical about it, they'll have a threat model. They'll describe what threats they're actually protecting against. So when it comes to encryption, the threat model may say, we're going to protect the confidentiality of your data, assuming and the attack surface of it is your private key and possibly algorithmic attacks on the encryption itself, but they may not be guaranteeing you integrity. If you want both confidentiality and integrity for encryption, you may want to have a backup scheme, or maybe you have unencrypted data in a physically secure location. So whenever anybody tells you any security result that they have, ask what their threat model is. What do they claim that they're protecting against? Are they protecting against a nuclear bomb blowing up your computer? Probably not. And so defenses are framed in terms of these threat models. And if I have time today, I'll actually go over some research that I'm working on where certain classes of attacks are solved, but it opens the door to other types of attacks because part of the surface that software security thinkers may not always be looking at. Okay, so these are just examples of threat models. So if you have a safe in your home and your safe has a key, you may share that key with a friend. And so you don't consider your friend a threat. You may have just a simple key on a thin sheet metal safe. And so your threat model is, well, I don't want sort of opportunistic attackers just opening the door and taking my money. But if somebody has, like a saw or a Dremel tool, well, they'll be able to easily cut through that. So if you're trying to defend against that, and as it says here, somebody may have some torch that can cut through, thick layers of steel or break through concrete. And so you need to be able to define what your threat model is. Is it defending against opportunistic attackers? Is it defending against a motivated attacker that has very robust tools? So these are just examples of threat models, and this is just pointing out that all of these defenses have a cost. And so maybe your personal diary that you treasure very much isn't worth, $100,000, safe room to do it. Maybe it is to you. But it depends on what the cost of the damage of losing that is. So for instance, for a bank, if some breach may cost them $1 million, but it costs them, $2 million to secure it, maybe they don't want to bother. Maybe they'll just be like, all right, oh well, we'll absorb that cost. Same thing in like credit card fraud. So companies just absorb credit card fraud, even though there are probably more robust things they could do to improve their security posture, which may also annoy their customers as well. So there are some common mechanisms, some kind of classes of mechanisms for information security: isolation, least privilege, compartmentalization, and trust and correctness. So one technique is isolation. So if you've got so for instance, in let me think of an example of this. So there was a, let's see if this actually applies. So who saw the XZ vulnerability? There was a recent very nasty vulnerability where instead of using one of these fancy software security exploits, which I'll show today, somebody basically just gained the trust of maintainers of a software security product. And they were able to create a backdoor in any system that installed this compression package. And the reason that was possible was not because the software that was backdoored, the SSH software that was backdoored, depended on it, but it's because they had an intermediary dependency. They did not have, I guess, proper isolation between these components. If you could have had stronger protections around these components, perhaps maybe you could have prevented them from overwriting each other's processes. If you haven't seen that example, that might not be a great example. Another way to think of it is, a bank vault. So if you go to a bank vault and you have a security deposit box, everyone's security deposit box has its own key. So if the banker can get in and one person can get into the vault, well, they still have to contend with the isolated, bank security vaults. So that's isolation. I couldn't think of a better example than those. Least privilege. So who here runs as admin on Windows or sudo as root? Who does that? Does anyone do this? Okay, so some people do this. So if you download some malware and you're on an admin account versus a non-admin account, the destructive power of that malware will be very different. So without having any exploits that will elevate the privileges to admin, they'll be able to install software, delete stuff, that system files. And so if you just move to an account that is not an admin account, you're applying the principle of least privilege. You give yourself the least amount of capability on your system as needed to do your job. So usually for most things you don't need an admin account. So the cost here is, well, I need to log out, go into another account. And so you can decide for yourself whether the information on your machine is worth it. But this is the principle of least privilege. Only give the capabilities or access that's needed to do the job. And so this could be people, and this can be computing components as well. So for instance, when you run certain applications on your machine, like just listing files, well, to list files, you need some access to the kernel to do that. Some other kinds of privileges, like opening ports on your machine that are in the privileged port levels. Well, you need root access to do that, but you don't need to run all of your users as root in order to have programs to do that. So Unix uses setuid and other techniques to do this. But anyway, that's least privilege. Also kind of need to know kind of fits into this. Compartmentalization. So this is similar to isolation, but the idea here is to allow for faults, but reduce the blast radius of those faults. So for instance, if you're, let's say you have a company where you have very confidential data and you have a website, if somebody breaks into your website, which is public facing, you really don't want that access to be able to give them access to your confidential internal data. So you want to compartmentalize, you could use firewalls or other techniques to compartmentalize servers from each other so that even if one is exploited, that won't bleed out into the rest of your system. This is kind of a cool example of a ship where they add several kind of air pocket compartments in the bottom of the ship. So if it hits an iceberg or something and water leaks in, it'll be isolated to one part of the hull. The whole hull won't be flooded. So this is much closer to the programming language world, where if you can prove the correctness of all of your components, basically that would also prove the absence of bugs. So this, if you take OS or you take security here, I think they'll go into this a little more. There are some existing techniques for doing this kind of software security on your machine. So the operating system itself, decades ago, was separated at the hardware level from access by the user. So this is why you have admin accounts or root accounts versus user accounts. Basically, the operating system itself runs at a special protected mode in the hardware that can touch your disks, it can touch memory, it can basically do anything with your machine. But when you're running in user space, none of that hardware is available to you. You have to go through the operating system kernel in order to access your memory. So it's kind of like virtualization. It provides a virtual layer on top of your hardware. So if, for instance, you want to run an application, you can't directly load it into memory or change the program counter in the machine. Instead, you call a function that then switches to the kernel, which then switches to the protected mode in the hardware and allows access to writing memory and changing the processor. There's tons of techniques in this. I recommend taking a software security class. There are ways to control access to files, which you probably know, like read, write, and execute access. There are more advanced versions of this, like access control lists and capabilities. And these can be used to do isolation. So even if a user can get into your machine, for instance, if you're not running it as an admin, they run malware, if they don't have an exploit of the kernel, they won't be able to do as much to your machine as an admin user would be able to do. And so as I mentioned, there are hardware techniques for doing this. So for decades, Intel, I think it was designed by Intel, they had these ring privilege isolation, privilege abstractions, where if you're running at ring 0, you have full access to all the hardware, whereas running at 3, you have basically no access and you have to go through the kernel. And there are other rings here for doing like virtualization and hypervisors. This is a little outside of the scope of this course. So access control, there's the principles of access control, and so this, it's commonly confused the difference between authentication and authorization. So these are techniques for managing access control. So even if you've completely protected your system, you have perfect confidentiality, integrity, and availability, well, you still need users to access the data. You need availability of this. And so in order to make sure the right person has the right access, there are several techniques for doing this. So one is, you're probably all familiar with, authentication. So for GitHub, when you made your SSH key, that key you use to authenticate to GitHub, that you are actually the person who created that key. Now, you may not be the actual GitHub user. If somebody steals your key, they can still authenticate. But the assumption is that as long as you keep your key private and you were the one who generated, then we can authenticate that it's you. This is different from authorization. So even if you can authenticate to GitHub that, yes, I am this user, if somebody else has marked their GitHub repository as private, well, you won't have authorization to access that. An audit is a little bit, probably something you don't encounter quite as much. But this is, for example, in a bank teller, if anyone's ever worked as a bank teller, there's very little protections on the bank teller from just stealing money. And it kind of makes sense, right? They have to handle cash and money and people's checks all the time. And so if there was expensive processes where you had to like authorize and authenticate, have some bank manager come in every time you take out $10, it would be a pain. So what do they do instead? They have extremely detailed surveillance of you as the teller. You're being recorded constantly. You have your cash box counted at the end of every day. There's video recording constantly. In some sense, there's more security on the teller than people coming in because of audit. So even if they do steal something, there'll be a trail to understand what happened and then presumably prosecute you or chase you down or something like this. But this is also a common technique that's used in security. For instance, in the famous Edward Snowden case, I think in part they were able to determine who had done this because they had audit trails of who accessed what systems. And so even though he had very broad access, very broad authorization, there was also audit trails that led to, that I think led to him, I suspect. I don't know how publicly this came out, but I think that's what happened. Anyway, so these are different techniques for access control. This is the kind of classic access matrix where you've got the people or users who have access, and you have the resources that you have access to, like files. And the classic two approaches here are access control lists, where for each file you have lists of users for each file, and capabilities, where each user has a list of things that they have access to. Anyway, this is some very, very fast overview of software security. If you're interested, there's HackUCF. There's a security class here. There's also a master's in cybersecurity to market this a little bit. But yeah, so in short, the glib way to say it is correctness is making sure a program does what it's supposed to do. Software security is making sure a program doesn't do what it's not supposed to do. And there are some classic principles to the different types of security that we want out of information: confidentiality, integrity, and availability. There's sort of no free lunch 100% security. It really depends on what your threat model is, depends on what your attack surface is, and so you can make security guarantees, or at least strong security assumptions, when you clearly define your threat model and do your cost-benefit analysis of the expense of using it, using certain security techniques versus the cost of having your security violated. And there's all sorts of techniques, hardware and software techniques for implementing the security of your software. All right, so questions on this? I know that was a very fast overview, but I wanted to give a little context for the demo that I'll show in the second half of the class. All right, so let's take a break. Let's take a 10-minute break. Let's come back at 11:05. Okay, so let's go over the main idea here first. So, well, actually, if you remember, we had this example program here that I showed probably a couple weeks ago. I don't know if you remember. But what is the output of this program? What does main return? What number gets returned in this program? Did I hear an answer? -7? So -7, so yeah, we're subtracting 8 here. What's the value of this, though? Yeah. Return 2. Okay, why? Why return 2? That's right. So to understand what your fellow student was saying, when we, let me do it this way. If we look at our stack layout, RBP is pointing here to the stack frame, and we've got space allocated for X and for Y, and in our compiler these are offset -8 and -16. So after we run x equals 1, then we move 1 into whatever the address of x is. The address of x is some offset from RBP. When we execute y equals 2, same thing. We find the compiler will compute the offset from RBP. And here, what's the address of x? Well, the address of x is this address, or I guess another way to look at it is it's this address here. It's here. This is ampersand x. It's a pointer to this part of the stack frame. So if I then subtract 8 from that, then Where am I pointing to in memory? Well, I'm pointing here. So this is the address of x minus 8. And so you can see that I can start playing around with other values on the stack frame. And this fact that local variables and other information stored on the stack frame has led to, and types of attack like this has led to an enormous number of what are called memory safety exploits, where you can exploit the fact that other important data is stored around some data you have access to on the stack, and you can actually do very serious things like execute arbitrary code or get root access on a machine just by manipulating values in memory in ways that are not expected by the original program. And these actually still make up a very large portion of software security exploits. Not this particular attack that I'm going to show you today, because there are protections against this exact attack, but attacks like it form a pretty large bulk of software security exploits. Okay, questions on this example? So let's go back to our stack again. And that was an example of looking at overwriting or inspecting other data that's on the stack. So in our case, X was here, Y was here. So this is part of our stack. What, if you remember, what value is stored at RBP? Does anyone recall the calling convention? Yeah.
The last location of Bitcoin?
The old base pointer, yeah, the old base pointer, the old RBP. What about before the old RBP? Does anyone remember what was stored here? Yeah. The return address, right. So if we could, we can not only mess with other variables, we could actually mess with the base pointer and even the return address. And so if we could overwrite the return address to jump somewhere else in the code, perhaps a call to shell, or that, assuming we have root access, then we could actually turn this program into one that gives us root shell access, if there was a way to actually do this overwriting. So that's the context here for the attack I'm going to show you, and this is the classic stack smashing attack that has been known and exploited for years. So there's I think this is one of the earlier illustrations of this. I don't remember what year this was, but this is at least a couple decades old at this point. And this post on FRAC, which was basically a software security or magazine, outlined doing this in a controlled way. All right, so let me bring up, so as I said, I'm an amateur at doing code exploitation. This is not my expertise, but I'm gonna try to get this right and try to show you along the way how this works. Okay, so let's take an innocuous looking program here. So here's the program. We print out this statement here, and we call vuln. And inside of vuln, we've got an 80 character buffer, and we read in 400 characters. Now, you probably wouldn't do this explicitly. This might be done through a string copy or other unprotected memory copy commands, but just for the sake of education. So by the way, I took all this from an existing website that you can go and I've listed on the site, this stack smashing tutorial, and they go into further attacks that can overcome some of the defenses. But this seems like a silly thing to do, but in practice this happened often from string copy, where string copy does not check the length of the destination array originally. And so this will read 400 bytes into an 80-byte buffer. So what's going to happen when we do this? What's going to happen if we try to, so let's say we've got our stack here, and we've got, I know we didn't go over arrays that much, but if we have a pointer to buff here, and 80 bytes, or 80 characters, and is this the only thing on the stack? There's also R, but R is down here. So this is our stack. We've got our stack frame pointer here, and our return address here. So if I do this read, if I read in 400 characters into buff, so this is where buff is stored on the stack. It's stored here, and then there are 80 or 79 characters above it. So what's going to happen to my stack if I read in 400 characters? What's going to happen to memory here? Yeah. Stack overflow. So what does that mean? What's our stack going to look like after we read in? Say I just read in 400 A's, the character A. What's my stack going to look like after I read in 400 characters? Let's assume we don't have any measures to prevent it. Yeah. So actually, with this code, no change to the stack frame will happen. Instead, what's going to happen is, let's say I just have 400 A's being read in. Then what's going to happen is this read command or string copy or other vulnerable functions will just start writing A, over and over and over. And it's going to do it 400 times. It's not going to stop at 80. It's going to keep going, and it's going to blow away the old base pointer. It's going to blow away the old address, and it's going to keep going, probably blowing away the caller stack as well, whatever that was. So that's literally what read does, or string copy, because you have free reign to write whatever memory you want in C. It's your own stack. You can just copy over whatever data you like. Yeah. Good question. So yeah, I forgot to ask which direction it would go. Why might it be writing up the stack? Yeah.
Initially, you allocate memory downward, and then as you begin the KFC array, you scroll from the bottom, which is the start of the array, and work your way upward.
Yeah, exactly. So if you do normal array or string operations, they're done in a positive direction. So if this is like 0 E1, then this is going to be 0x E2, 0x E3. So normally when you're doing like array operations, you're going positive offsets. But our stack grows negative. Our stack grows down. So this is offset negative 80 or whatever it is, whatever it's going to be. So memory operations like string copies, memory copies, these are going to go positive in the memory direction. So that's why it's growing up the stack, because the stack grows downwards. And so it blows away whatever's above it on the stack. So let's see this actually happening in practice. So I've got this. This is all from that website. Feel free to encourage you to kind of do this on your own. Try doing this on your own. So here's a Python program that will just write out 400 A's. So here's my 400 A's in a this is. There's my 400 A's. So let's see what happens when we actually run our program in GDB. So I'm just going to run our program here. I'm going to set a breakpoint at line 13. So where was line 13? Well, okay, so I can probably break earlier as well, actually, to see it happening. And let me run the program passing that text file in. Actually, let me break it. Let me break it earlier. Let me break at vol. And let's run with our input here. Oh, I should have done. I did do debug. Okay, so it's a little hard to see where. So this is the input processing. Here's the read command. The read command's gonna take a long time. Oh, this is why I broke. This is why I broke at 13. Okay, but anyway, this is after we have done. This is after we've. This is on line 13. So after we've done this read, you can see, if you see the stack here, we've got A blowing away everything in the stack, including our return address. And if we continue, then we're going to get a seg fault. And why do we have a seg fault? So the last instruction we ran was return. What happened? Why did our program crash? Yeah. So the return address was overwritten. So there is a return address. It's just that the return address is, it's A, basically. So here is the, these were the save registers beforehand, but this was the return address that we overwrote. So 41 is ASCII hex for A. And so you can see if I had a non-vulnerable run, it would return back to main, just like in your compiler. But because I've blown away the stack with all A's, using, this was what our stack frame looked like, by reading over the bounds of this 80 character buffer, I've overwritten the return address with just a bunch of A's. The return address is more than 8 bytes, or 8 bits. So it's like, a sequence of 8 bytes. And so I've blown away my return address. Questions on this? Does this make sense? Why this happened? Okay, so you can see that this actually does happen in practice. You can actually blow away your stack and cause. This is the name. This is the namesake of the site Stack Overflow, or actually Stack Overflow is that's from too many stack calls, actually, not this. But yeah, you can see how we can actually, just with normal C functions, we can blow away our stack and blow away our return address. All right, so we could crash our program, but that's kind of interesting. We can cause some trouble, get this segmentation fault, instead of just reading in 2 bytes and finishing the rest of the program. But how can we exploit this to run whatever code we'd like? So this PDA GDB debugging framework that I recommended you guys use has some facilities for helping us find information about the stack. So where in the stack the return address is. So if we want to be able to point the return address to some code that we'd like to run, the first thing we need to do is figure out how to not just blow away the return address, but target it, be able to figure out where in the stack it is. Now we could sit down analytically and try to count how many stack frames there are, play with the debugger. But this framework has some useful tools for doing this. So it can create a pattern of characters that will allow you to read a number in that memory location and then figure out the distance in the pattern. Again, this is outside my expertise. I'm just using this tools. But basically what you can do is you can run on this pattern here. So this pattern looks like a random sequence, but basically it knows deterministically how far down the pattern it's like you can think of it as a random, unique sequence of characters, and in GDB you can figure out from that information where in your stack, how far away from buff your instruction pointer is. So this is the content at the stack pointer. This is generated from the pattern. And so what we can do is we can where is this code here? We can use that information in order to tell us how far from buff our instruction pointer is. So this is how far away from the instruction pointer we are. So now I can instead target knowing that I have an offset of 104 for the instruction pointer. I can generate, instead of 400 A's, I can generate 104 A's, and then put something different in the instruction pointer, in the return address. So here I'm going to put B instead, and then C. So this will be 104 A's followed by 8 B's, and then the rest are going to be C's. So I'm going to blow away my stack, but instead of just blowing it away with all A's, I can target the return address with some very specific code. And so this will prove that I can insert I can overwrite specifically the return address. Yeah. Yeah, you could. Yeah, it is. Yeah, I think you could call this an injection attack. Usually that's like, database injection or like logging injection. But yeah, in some sense, yeah, it is like an injection attack, and we're going to inject additional code into the memory space so that we can actually run that additional code. But in order to take control of the return address, we first need to figure out where in our buffer to modify in order to overwrite the return address. So going back to our diagram, instead of just generating all A's, we're going to generate all A's and then a sequence of B's at a very specific spot, so that here, when we get to the return address, we're going to be able to target it with a new address. Now, right now, we're just going to use B's for that address, but we'll see later how we can pick our own address to run code that we would like to run. So right now, we're just trying to figure out where in the stack our return address is. And so using these tools from this exploitation toolkit, we can do that empirically. We can figure out that it's 104 characters away from buff. Okay, so let's see what it looks like when we use our new input. So just to show you what this looks like. This is our new input. We have 104 A's followed by 8 B's, and then the rest are C's. So when we go to run this case, we should see that our instruction pointer that we just overwrote is all B's. So what should have happened is we read in each character. It overwrote everything on the stack and just overwrote the return address with B's. And so we can see in our output of RIP that RIP indeed is now set by us, by our input. Make sense? Questions about why that happened? How we were able to overwrite the instruction pointer? So when we had the buffer overwrite, we targeted the spot on the stack that held the return address. And when the program went to execute the return instruction, it instead tried to return to B instead of what the old return address was. And so when you return from a call, it's updating the instruction pointer to be whatever was on the stack. So it's kind of the consequence of mixing code and data. Because this is supposed to be data, not supposed to be something that's executable, but information from this stack is used to control the execution of the program, namely the return address in this case. All right, questions on that? Questions on that so far? How we were able to take control of the instruction pointer? So all we did was exploit the fact that the stack frame holds the return address, and we used the buffer overwrite to overwrite that return address, and when the function returned, it returned to the address that we specified instead of the one the compiler wrote, or the call instruction wrote. All right, so it has an unfortunate and aptly named register, RIP, like you're owned, you're dead, as soon as you can do this. Now, the tricky part is, how do we use this to run arbitrary code? And so there are lots and lots of ways this happens. You could put, instead of writing C's here after, so right now our code writes C's, instead what you could do is you could insert the machine code for some code you'd like to run. And usually, if you're trying to take control of a machine, you want to have arbitrary access to it. One convenient way to do that is to have a bash shell, to have a shell. And so this machine code that gives you shell access is called shellcode. And you can get it by basically writing a small assembly program which will call out to the system call, which will execute the shell program, and then just assemble it into machine code. So as I think you know now, that any binary like the program we compiled, it's just a sequence of machine instructions in binary. So if I were to disassemble this, so assembly code just gets compiled into binary instructions that are read by the machine. And just like any integer or pointer or struct, it's just data. It's just binary data. And our exploitable program allows the user to read in any kind of data it likes. And because we have this buffer overwrite, we can store shellcode in the stack. So that's one way to do it, is you bundle the shellcode with your input. The attack specified on this page is a little easier to pull off. So the problem with that is, how do you find the address of the shellcode? That's a tricky part here, because the address may be different. So the attack on this page uses a simpler approach to get this shellcode in memory, and it does it using Unix environment variables. So Unix environment variables, and they have these in Windows as well, these are basically system-wide data that hold some useful things for running your system. So probably the most common one you've seen is the path. So there's this environment that just holds a set of variables that hold values that are used by the system. So for instance, if you want to get the current working directory, you can use this variable if you want to know the shell. If a program wants to know the current editor, if it wants to know the home directory, these are all stored in kind of system-wide variables that the user programs have access to. And one of the most famous ones is the path. So this is why when you compile your own program, you have to write // in order to run the program, because whenever you just put a name, the system, the shell, will look up that executable in the path. It'll look in each of these directories and say, where's that program? But if you give a full path to a program instead of just its name, you can execute any program you want. So this environment, this has been the source of lots of security exploits. There was a famous one in Bash where you could overtake, I think, a remote system by playing with environment variables that get set by a web server. But so what we're going to do is we're going to take some existing shell code. So this is the binary shell code encoded in C's escape character-based characters. So, normally when you write a string, you only have access to the ASCII characters. But there are escape sequences in C where you can encode the string as hex numbers. And this can be done in Python, in any language you need. You basically just need to have an input file with that binary machine code in it. So any compiler or assembler does this. It just needs a way to write it into binary. So here we've got this shell code where, so this is just a Python program which will print those binary characters out for us and store them into an environment variable. So that's all this code does. So if we look at, try to print this shell code, it's going to kind of look like gobbledygook because your terminal is not able to interpret some of this binary data. You can pass this to like OD or other related tools to see the value of this, say in hex. So this is the sequence of data we have in our shell code in hex. And I don't know I wish I knew how to disassemble this. Actually, can I disassemble this? Maybe need to be linked in order to disassemble. I don't know if this will work. No, it has to be in the right format. But if you were to disassemble this, you would see something like this sequence of assembly instructions. Something like that. Okay, so we've got our environment variable set up with shell code. And the way the environment variables work is that every program that's executed gets a copy, or at least access, to these environment variables in memory. And there is a C library for accessing environment variables. So in this program, we can get access to whatever variable we want, whatever environment variable we want. All of your programs that run on Unix have access to all the environment variables. So it has access to the path, your home directory, the working directory. And this program here will tell us where in memory that PWN, that pwn environment variable, is being stored. So this is just some pointer manipulation code that will give us the address of that pwn variable in memory. Oh, target program name. So this will tell me that, so it'll basically, it'll load it into memory, and then, so that the environment variable also stores the name of it has the name of the program as well. But this will compute the address in memory of pwn whenever I run classic, whenever I run this program that I've been trying to exploit. Okay, so to bring this back to our buffer overflow, so what's going to happen is our system will set up this big address space for our program when we run classic. And somewhere in here, there's going to be the environment, and somewhere in the environment is going to be the PWN environment variable, the pwn environment variable, and this is going to have our shell code. Our shell code is going to be in memory in the memory of our classic program when we run. And somewhere here near the top of the memory space is going to be our stack frame. So when we call vuln, there's going to, our RBP is going to be pointed here, and in here is going to be the stack frame for vuln, and in that stack frame is going to be the return address. That return address is going to point to, originally it's going to point to main, because that's the caller. So this is the original return address of vuln. It's going to point to main. And because now we have control over the return address, we can overwrite it. We can overwrite it to then instead jump to our shellcode. So if we can put all those pieces together, we can run this program, give it an input that overwrites the return address, set up the environment so the shell code is in the memory of our running program. And then we can, basically when we run our program and give our specially crafted input, we'll have a shell. Questions on this? This kind of makes sense? So now this is a pretty rudimentary attack, so there are protections against this already. But the key is, if you can get shell code into memory, and you can alter the flow of control of the program, then you can run whatever you like. And the dangerous part about this is if our program is running as the root user, then not only will we run whatever code we want, running a shell, we'll also be running a shell as the root user. So without getting too much into the permissions of Unix, here I have the program owned by root, and there's a feature in, well, I don't know if you consider it a feature or a vulnerability, but in Unix, certain programs, you need them to run by the user, but the programs need to initiate the execution of the program, but in order to do their job, it needs to be run by root. So any sort of mount or other programs where the user may have authorization to do certain activities, but you don't want to have them run as root, there's a system call called setUID, which you can use to change the user to root during the execution of the program. And so this has been fraught with problems for decades in Unix. There are all sorts of mitigations to this. But in order to make this work, this program needs to be owned by root. Yeah, go ahead.
So if you just set the user to root of that program, what's preventing you from saying that the user root is that any arbitrary program?
Wait, say again?
So if you can just set the user to root by saying the ID.
So there's the ownership of the file, and then there's the setUID function system call. So for instance, if we look at all of the programs you commonly run in this system, they're owned by root. And so usually they're being run as the user who asked to run them. So you don't need to run like GCC as root. So even though it's owned by root, when you run a program, by default, it's going to be running as the user who ran the program, not the owner of it. But there are certain things, certain utilities, where it's useful to temporarily run as root to get some job done, and then go back to running as the user. So for instance, reading your mail. Your mail may be stored in some place that only root has access to, or doing some server maintenance. And so the set, this is like a, you'll see it's all about exploitation. There was an old paper, I thought it was setUID considered harmful. Am I remembering this right? So I can't find, there was an old paper talking about exploits around this. Yeah, I mean, you can see in the manual for it, so, it allows someone other than root to kind of temporarily elevate to perform a very specific task. But if the program's owned by root, then the user can't rewrite the program because it's owned by root. So it's basically saying this section of code is allowed to be run by root. And as long as that's correctly written, and the user can't overwrite that code, then it should be safe. It should be safe to do that. The problem is if I can inject arbitrary code into a running process, then I can run as root. Yeah.
So do any common programs use this? Because none of them, I don't think they do. None of the floating programs use it. I want to use the mount program. I have
To run as, it might be by group. So sometimes it's set group as well. Might also do it. So if you have an admin group, I think you might be able to change permissions to do that. Let's see. Yeah, who uses set UID? Okay, so what programs use set UID root? Oh yeah, password. So when you want to change your password, that's a classic. Yeah, that's the classic example. Because it's changing a system file that no one else should read. So if you want to be able to change your password, you have to temporarily, the root has to do it. So yeah, that's a classic. That's a classic one, I think. Actually, there's a way to. I can't remember how to see this. There's a way to inspect whether it has the. So these permissions have since been improved. Oh, I think it's this. I think this is the. So I think it used to be the case that you could just call set UID, and if it was owned by root, then it would just change to root. But I think since they've added a special permission, you have to explicitly put the set UID to root permission on an executable, and I think that's this. I think that's what this S means. It means that this program. So actually, that means that we can actually find all of the programs here that have the set UID set here. So here's everything that has the set UID set. So mount does, I guess, because there may be a way to add, there may be a group, maybe a way to add users that have mount permission, I think. But yeah, that's a good question. So yeah, thanks for bringing that up. Why would you actually need this? And so here are the examples of where they have this the set UID bit set. Yeah, that's a good question. There just must, I can't remember, but there must be a way to let users, non-super user mounts. All right, we're getting off into sysadmin stuff, which is also outside my scope of expertise. So you can say, this is system level stuff, but basically you can say certain drives are allowed to be mounted by the user, I guess. And I guess that's why. You have to, yeah. We're getting way outside of the UX, but I think you can, I guess mount will allow non-root mounts. But anyway, so the point is there's some features, there's some functionality like changing your password, where you don't want users to just edit this password file, but at the same time you need them to be able to touch some things in the system. And so the kind of classic Unix way to do this is to there's this system called set UID. which you can just say, I want to change myself to the root user. Now the program has to be owned by the root and has to have this set UID bit set. But if you can exploit password, if you can inject code into password and overtake the return address, then you could basically run a root shell, even as the root user. So this is called a privilege escalation, where you violated this, the isolation and security authorization in order to access in a privilege level that was not intended by the system designer. Okay, yeah, good questions. So to bring this back to where we left off, here's buff. So this is the stack when we start executing vuln. Here's buff. It's going to read in our input file, and our input file contains a sequence of 104 A's and then contains an address, which is going to overwrite return address. And that address is going to point to the shell code that we injected via environment variables. And so when we run this program, we should see that transfer of control flows to this shell code. And when we do that, it's going to execute sh, it's going to execute shell. And because we've already, in this version of the shell code also runs setuid. So the shell code will run setuid to root, and then it'll run shell. It'll run the bash shell. It's okay. So let me see if this actually works. So I guess just to show how the code was injected. So this is how the code was injected into the environment. And then this is how we got the address. We ran that get veinvent. And then the exploit code just needs to just put 104 A's, doesn't matter what it is, and then overwrite the return address with the address of our environment variable, which holds the shell code. That was what we found by running get event. So this is the address. So this was the location in memory of the pwn variable, which holds our shell code. And so we overwrite our instruction pointer with that code. And when we go to return from that function, it should just give us the shell code. So let's take a look at this. Let's break where can I break at? Oh. Okay, let me just run the attack, and you'll see the segmentation fault. I have a pre-computed one that I hope will work. Oh no, it doesn't work. This is what I was afraid of. All right, let me go through the actual steps of doing this. Okay, so here's our exploitable code. Let me get the address of the. Okay, so it's at a different address. I think because so the address of the shell code is different now, probably because I modified my environment variables are different. So I need to update the address here. So this is the address that I need to overwrite my instruction pointer with. So it's different from when I was running this last night. I need to generate that input file. So here's my new input file. That should be the address. And so hopefully, when I run it this time, okay, there we go. So now it's running the shell code. It ran the shell code, it did set UID root, and it ran shell, and now I just have a root shell. And who am I tells me what the user is, and I can do all sorts of nasty stuff, like touch a root file on the root file system. And there it is. Okay, so there's the attack. Finally got it to work. So this is what's going on. And the shellcode, if you want to see like more about shellcode, there's a website that just like lists lots of different shellcode for like everything. So if you could find a way to inject your code into a running process, and you can find a way to overwrite that return address, then you're golden. And you have a set UID. You could also run as other users, I guess, if they own that code or you're running someone else's program. Now this kind of attack has since been mitigated. So in order to do this, I had to turn off a technique called address space layout randomization. So the fact that I could get the address of this to work every time, like to be the same every time I run the program, that's because this address space randomization was turned off. So this feature is don't turn this off in your operating system, leave this on. If I turn that feature back on, you'll see the address of the environment variable changes every time I run. So I wouldn't be able to statically know what the address is. Now there are techniques where during the exploit, like you can figure out that address. You could somehow have shell code or code that would figure out that address. But of course, if you could do that, then you already have code being inserted. There also are detections against overwriting the stack. And to handle these, people have developed return-oriented programming. And so this is instead of inserting shellcode or overwriting the stack, overwriting the stack with code that you want to execute, instead you piece together a shellcode from code that's already in memory by modifying a sequence of return addresses. This is a super complicated attack, well beyond my capability. But basically, and there are frameworks for doing this. So because there's a lot of standard library code in memory already, you already have pieces of shell code that you can construct by just altering the return address of several different pieces of your call stack. And then you can basically compose together what is shell code just by manipulating return addresses. And of course, there are defenses against this. There's control flow integrity, which will prevent return address attacks, and then there are other attacks that get around control flow integrity. All right, so questions? Questions on the exploit? Yeah.
Can you just briefly explain how we're changing where the return address is going?
Yeah.
And also putting the value that we're returning?
So you mean the value of the shellcode or the value of the return address?
Well, we're changing the return address, and then I just don't get how we're putting the shellcode.
Oh, the shellcode. Okay, yes. Maybe I didn't cover that well. So we put the shellcode in an environment variable. So this environment variable holds things like your home directory, the path, the current path, and it's user writable. So we put that shellcode into the environment, and if you look at how programs are executed, at least in Bash, in your shell, they're going to be executed with basically a copy of this environment. So every program that runs will know the home directory, will know the current user, will know be able to get that information from the environment. Same in Windows. I think they have environment variables as well. And so you can see here that when you run the system call to execute a program, or at least the one that's used to pass the environment in, the environment will be basically copied into the memory space of the running program. So that's how we were able to get. It's kind of a roundabout way to get this into the memory space of the running program. Because this environment is just always copied in from whatever is set in the environment, whatever environment variables are set. And so by setting the shell code as an environment variable, we ensured that code would be in the memory space of our running program, and any running program that we run from the shell. Does that answer your question? Well, it's guaranteed that code will be in memory. Running it, though, you have to overwrite a return address to make sure it'll jump back to that point in memory. And so this attack can be, at least specific attack can be handled by just making sure you just randomize the layout of memory. You make sure that this environment variable is not always stored in the same spot for every execution of the program. So when the loader sets up the memory layout of the running program, It just randomly puts the segments in different spots in memory, so you can't predict statically what the address of that, even if you had shellcode in there, it's still going to be in there. But so just because you have vulnerable shellcode doesn't mean you can actually execute it. And so in this particular attack, we depended on not having that address failed landerization, so that we could predict ahead of time what the address of that shellcode would be. Other questions? I think was there another question? Yeah. No.
It's like the thing in GCC, I think like basically what it does, like just have to check it up further before I remember, but it just like stores a copy of the call stack.
To make sure it's the same after you. I guess an attacker would then have to modify the shadow stack too, but maybe it's hard to find. Yeah, I see. Shadow call stack. There's the shadow call stack. Only supports, it's only ARMS 64? Okay. Other techniques are, so sometimes shellcode is written into the stack, and so you can, at the hardware level, specify the read, the write, XOR, execute bit. You can say that memory should either be written or executed, but not both. So that way, this code if you get code in the stack and you mark it as write or execute, it won't be executable. You'll get a hardware trap that'll say, hey, you can't run this. So that's why the environment variable, I guess you'd have to set that as well to read, write, or execute, but this doesn't. But anyway, so it's a big space of security. I'm by no means an expert, a comprehensive expert, but I just wanted to show that this understanding of how the compiler works, how it works with the system, will allow you to understand these software exploits and maybe find your own exploits. All right, so let's leave it there, and have a good weekend, everyone.